All right, there's a question asked. This is from Nabi. How to do question 7 for CA3? Now, this is the question 7. Nabi, is this a question you're asking? You look at the screen, number 7. Okay, you're asked to plot actual number of trays, condensers, and reboiler duties. Now you find that in your Aspen results, your condenser, the answer is negative. A reboiler is a positive number. Ignore the negative number for condenser. Negative means heat is taken out from the fluid. Positive means you're adding heat to the fluid. So when you do the plotting, don't put in positive, negative. Treat the heat duty for condenser as it is. Forget about negative sign. And you're plotting the actual number of trays, condenser and reboiler duties against the external reflux ratio. Now, the external reflux ratio, you remember that is 1.2 to 1.5 times the minimum reflux ratio. A minimum reflux ratio is 0.8 something. You check that in your Aspen. Then you times the 1.2. You run the simulation, you get an answer. Condenser, reboiler duty, and the actual number of trays. After that, you change the multiplying factor to 1.25. 1.25 times the minimum reflux ratio, and then run it again. Then you change it to 1.30 times the minimum reflux ratio and change it, and then get the results. And do it until you reach 1.5 times the minimum reflux ratio. Then you can plot, same plot, in the same plot. You can see here, that means one graph. You can plot a few lines on the same graph. It can be done. You just have to look carefully at the data series. Data series, some of the location of the cell on the Excel spreadsheet, you can manipulate, can change it, and then you can plot the actual number of trays, condenser, reboiler duties against the external reflux ratio. Now, external reflux ratio means condenser.
Hello.
Okay, you can use all right, instead of 0.05, I know you want to use 0.1. I suggest 1.2 times the minimum reflux ratio, 1.25 times the minimum reflux ratio. If you use 0.1, then you don't get the resolution. The resolution means you don't see the fine details, how the condenser duty, the reboiler duty, and how the actual number of trays change when you change the external reflux ratio. So do it more slowly by using a step size 0.05, 1.20, then 1.25, and so on. Of course, you can use 1.20, 1.22, 1.24, 1.26. You can do that. So using a smaller size will be better. You get a smoother curve. Okay, section B, question 7. Okay, one by one. Now, question 7, state and explain a change you want to make to your column. Perform the change, evaluate the results, and draw a conclusion. Now, this case, our original design objective is to obtain 96 mole% benzene in the distillate. Remember, 96 mole percent benzene in the distillate. This is the design objective. Now, example for change. Now, let's say you want to increase the purity. You can say, okay, now my design objective is to obtain 98 mole percent benzene. Define that. You have to make some changes in your Aspen definition. You can see that there's one part where I explain what is the light key, what's a heavy key. Light key for the bottom product. Heavy key is for the top product. So you make some changes, increase the purity of benzene in the top product from 96 mole percent to 98 mole percent. Now, for the case of the heavy key in the distillate, the heavy key in the distillate is toluene. All right, toluene. So instead of 0.04 for toluene, you change it to 0.02. Now, if you change for the heavy key toluene 0.02, it means that 0.98 is for the benzene. And then you run the simulation, RUN, there's a button for it. And then you look at the effect. And from there, you can look at the effect. So what is your hypothesis? Hypothesis is that if I increase the purity of the benzene from 96 mole percent to 98 mole percent, my hypothesis is that the reboiler duty will increase because now there will be more liquid, for example, and the condenser heat duty will also increase, assuming that you keep the same number of stages. So assuming now you have 19 or 20 stages, you keep that. And then you explain the outcome. And another example is that you want to change the reflux ratio. You can do that. You change the reflux ratio. And what's your hypothesis? Increase reflux ratio, distillate flow rate decreases, and therefore the column temperature will decrease. Column temperature decrease, more liquid flows down from tray to tray, and more liquid enters into the reboiler. Therefore, reboiler heat duty will increase. And what happened to the purity of benzene? You expect the purity of benzene to go above the 96 mole percent. And that is expected. So that is your hypothesis. And then you check against this hypothesis. All right, Zachary. Let me answer Zachary first before I go to the section B, question 6. Now, if you want to modify the tray geometry, then what kind of geometry you can find in Aspen? Are you going to change the weir height? Are you allowed to change that? Or are you allowed to change the plate diameter or tray diameter? Or are you allowed to change the tray efficiency? Okay, tray diameter. So if you're allowed to change tray diameter, you can try that. You see what's the effect. Like increase diameter, don't increase too much. Maybe increase 10% or 20%, or decrease the tray diameter 10%, 20%. Don't do it for 50%. Just 10% or 20%. Let's see what's the effect. Question 6. Section B. Now, based on the hydraulic plots in 4C and 4E, evaluate whether the tray encounter flooding or vipping. Now, this one I got to refer to the revision slide. The most important slide is the last slide. I mentioned there's a long question for distillation column. So the last slide is the most important one. You can see here, this orange line. Now this is, y-axis is the vapor mass flow rate, kilogram per hour. So y-axis is vapor, x-axis for the liquid mass flow rate. As long as your operating point is between the purple curve and the dotted pink line, 0% VIP and the maximum entrainment, as long as between these two, within this envelope, then we are safe. Safe in the sense that no flooding and no vipping. Definitely, if there's no vipping, definitely there's no dumping. So you check this one from your Aspen. So from there, you know whether this operating point, but you have to check tray by tray, as what I did in a class. If there are 20 tray, you have to begin with first tray, second tray, and so on, until tray number 20. Check it one by one. All right, it's good that David understands this. You have any questions on the theory part? Richard, you're very quiet. All right, there's a question, section B, question 2. All right, this one I've explained this morning. Explain the difference between sizing and rating problem of distillation column. Now, sizing. Sizing is when I do not have distillation column, I'm thinking of purchasing one distillation column. So I specify design objective, for example, the 96 mole percent benzene purity or 99 mole percent benzene purity for the distillate. So I specify this one. I know my feed condition. I know my temperature, my pressure, my feed composition, what's the molar flow rate of benzene, what's the molar flow rate of toluene. And I know the feed condition. Is it a saturated liquid, subcooled liquid? Is it the saturated vapor? Or is it a mixture of liquid and vapor? Or is it superheated vapor? So I know all these conditions. Then from there, I run the simulation. And the sizing will tell me, first I do the shortcut method, which was developed by Underwood. And then after that, I continue with the second stage. There's a rigorous calculation. The rigorous calculation in Aspen is known as distillation column. And then from rigorous calculation, I know that the plate diameter, I know other information. I know what's the weir height. I know what's the path length. I know what's the flow path. I know what is the top down comer area. I know what's the bottom down comer area, and so on. I know the hydraulic of each tray. So that's called sizing. Rating is different. Rating is when you suspect there's a fouling. You suspect there's a fouling, and you key certain information. For example, because of you suspect there's a fouling, and the company chemist from the distillate and found that the purity of benzene is not 96%, maybe it's 94%. So you collect all the data, and then all those relevant data you key into the Aspen, and then you run the simulation for distillation column based on the existing number of tray. Because now the distillation is already there, it's fixed. So you know the number of tray, you know the feed tray location. But now the purity is different. Then you run it, then you find that, oh, to achieve the 94 mole percent benzene purity, you don't really have, don't need to have so many tray. Then you know that there's definitely the separation efficiency is lower, is lesser than expected. Now this is an example of a rating problem. Yes. Okay, so Min Kang. So in this case here, if you increase reflux ratio, now remember the mass balance, the reflux flow rate plus the distillate flow rate is a constant. It's a constant, assuming all the things are unchanged. So if you increase the reflux ratio, the reflux flow rate, now remember reflux is a cold one, distillate is also a cold stream. Cold stream because they come from the condenser, so must be cold. So when you increase the reflux ratio, you're putting more of the reflux back into the top tray of the column. Now, as a whole, the overall temperature of the column will decrease from tray to tray. It will decrease. Now, when it's decrease, what does it mean? So now you have more liquid flowing from first tray to the second tray, from second tray to the third tray, and so on until the last tray. More liquid. Now this liquid flow rate internally is known as the internal reflux flow rate. More liquid will then go to the bottom of the column, and more liquid will enter the reboiler. More liquid enter reboiler, so reboiler heat duty will increase. So reboiler heat duty will increase, more vapor will be formed. As a result, more vapor will flow from a bottom tray all the way to the top tray, and then above the top tray, you have overhead vapor, more overhead vapor go to the condenser. Therefore, condenser will condense more vapor. Therefore, the condenser heat duty will also increase. So this is what happened. All right. So, yeah, Iman. So is finding the geometric shape of column inner components like rear height and hole placements counted as sizing or rating? If you're doing it, in our case here, it's a sizing problem because we don't have distillation column in our case. But if you really have a distillation column, then you're doing it as a rating problem. So so it depends on where we are now. Are we starting from scratch? That is called sizing. But if you already have a distillation column, then we are doing a rating problem. Do you have any questions on the fluid flow? Yeah, for sizing, that is correct. For sizing, in a way, no column. Yes, it's true, no column. But we know the feed condition. We know our design objective in terms of purity of the benzene that we want in the distillate. So we start from scratch. There's no column. We got column, we call this rating. So rating, our column is there. As I mentioned, we got problem with fouling. So you suspect there's a fouling on many trays. And therefore, the purity of the benzene is no longer 96 mole percent, is below 96 mole percent, maybe 93, 94 mole percent. And because we suspect that, then we do a rating. When we do a rating, in fact, our hypothesis is that separation efficiency has decreased. So we do a rating, and then from there, from a plot, we know the K factor. Remember the Y equal to Kx. You look at the K factor. So we find that, oh, the K factor somehow has shifted. The whole curve has shifted. Then we know that our separation efficiency is affected. So if you compare with a brand new distillation column, the K factor versus the tray position, and the old distillation column, K factor versus the tray position, you see the two curves don't overlap. The two curves don't overlap. We know that definitely there is a deterioration in the separation efficiency. So that is an example of rating. All right. So you can type your questions, Zachary. Anybody want to speak? I can allow you to speak if you have a mic. I can unmute. Eldred, do you want to speak?
No, Dr. Lee, I don't want to speak.
Okay. Yes, as long as the operating point is within the boundary, then we are safe. Now, if we recall this one here, as long as we're in the boundary, then we are safe. So we look at this one. We are between the maximum entrainment, 0% VIP, then we are safe. Okay, as in this case here. This is the operating point. This orange line is for constant vapor mass flow rate to the liquid mass flow rate. As I mentioned, this is the limit for 0% VIP. Now, if your vapor mass flow rate goes below this dotted line, then the liquid will find opportunity to pass through the hole. If you think of a sieve plate, then as we decrease the vapor mass flow rate, the liquid drop now becomes continuous flow. So then your continuous flow rate will increase until it becomes very vigorous. It's very vigorous, then we call this dumping. Dumping is like a liquid that's flowing down without resistance through the holes. Yes, in this case here, it's fixed for each tray. This is, in this example, tray number 37. It's fixed. But when you go to another tray, then you have to check. You check the vapor and the liquid flow rate. You check the flow rate. Then you go to another tray. You find the ratio may be different. A tray 36 or tray 35 or tray 38. You may find that the ratio here is different. So when you check the hydraulic plot, you check tray by tray. Now, by convention in Aspen, 0 is condenser, 1 is the top tray, because you're using the top-down numbering. If let's say the last tray is number 20, then the 21 refers to reboiler. Leonard, you have no question? Leonard, do you want me to unmute? Anyone want to speak? Let me know. Do you have questions on the revision slides? Any questions on the exercises? Any question on exercises or tutorial? Now we look closely on the plate diameter. Now this is the diameter of the plate. The VF is equal to K times the square root term. Now this K depends on plate spacing. Spacing means trace spacing between this plate and the next plate. What is the distance? The stream flow rate means vapor and liquid flow rate. Density means vapor and liquid density. So you see that 70% to 90% of VF. And this one I already explained this morning. If you increase the spacing, let's say the K factor is here. If your spacing is 0.30 meter, increase it to 0.60 meter, your K factor becomes bigger, your VF will increase. This one makes sense because if your VF increase, that is because of the bigger tray spacing is taller here. As imagine you move up here, spacing become bigger. Therefore, it can this one has more room for for the liquid. But when you do your calculation, remember that we use a factor 0.85. Now, if 0.85, your area is more than expected. Instead of just doing QV over VF. So now divide by 0.85, your area increased. Your area increased means your tray diameter increased. This is to allow us some margin of safety as far as the flooding is concerned. No, except that I mentioned that there will be 6 short questions. 1 short questions, 10 marks. Now for the short questions, focus on the calculation part. The calculation is important. I mentioned this morning about pipe connected in series, pipe connected in parallel. Yeah, important. And for the long question, there's 1 long question installation and 1 long question on heat exchanger. So you study the CA very carefully. In particular, distillation, this plot is very important. All right, this plot, you must know how to interpret the plot. And secondly, you must understand how the sizing is being done. The sizing is really based on 2 things, the 2 extremes. One extreme is the flooding. The other extreme is whipping. Whipping is for very low vapor flow rate. The flooding is for very high vapor flow rate. The vapor flow rate is high. It will create a lot of bubbles, a lot of gas bubble inside. It will cause the volume of the liquid to increase. When volume increase, just imagine that the liquid level is rising. This is like rising water. And you think of a river water. If the river water rises too much, then the river water will flood. It will flood the surrounding, flood the road, the house, the gardens, and so on. Now, question 7A. Are you referring to the section A or section B? This one I already mentioned. State the change that you want to make. So you can change reflux ratio. You can change that. You can change the purity of the product that you want. Currently, our purity is 96 mole% for benzene. There's one place where I demonstrated in the class. The heavy key for top product is the toluene. So toluene in the top product is 0.04. If you want to increase the purity of benzene, let's say to 98 mole%, you change the 0.04, bring it down to 0.02. That's for toluene, 0.02. It means that benzene purity now you want it to be 98 mole%. And then you run the simulation and see what's the effect. Is there any change in the column diameter? Is there any change? Is there any change in the reboiler heat duty? Any change in the condenser heat duty? Is there any change in the K factor? You can see a K factor. Any change in the temperature profile? So what is your hypothesis? So your hypothesis is that, okay, so now I want higher purity. Therefore, I expect the condenser heat duty to increase. I also expect reboiler heat duty to increase. And then once you have this hypothesis, then you look at the actual results from your simulation. From there, you know whether your hypothesis is right or not. But the important thing is not whether your hypothesis is right or not. The important thing is that you know what you're doing. Do you understand what you're doing? If you understand, it doesn't matter whether your hypothesis is right or wrong. You can still explain. You can still explain the outcome, which is part D. All right. So his question is, state the change that you want to make. Iman, I quote example. Currently, our design objective is to achieve 96 mole% purity for benzene. And in the simulation, the top product, heavy key, is toluene. The bottom product, light key. Light key means the most volatile component is benzene. Now we only focus on that particular objective. The heavy key, which is toluene, in the distillate, the top product is the distillate. We want to change the design objective from 96 mole% benzene to 98 mole% benzene. So we increase the purity from 96% to the 98%. So what is your hypothesis? So your hypothesis could be condenser heat duty increase, reboiler heat duty decrease. So condenser heat duty increase, reboiler heat duty decrease. So don't bother about the hypothesis. Then you run the simulation. What's the outcome? Then you explain. Oh, one of them is right. The other one is not quite right. Then you explain why is that so. And then part E, you share one learning point. What you learn from this simulation. From this simulation, you learn, for example, changing the design objective in terms of benzene purity will affect the rate of heat transfer in the condenser and the reboiler. And not only that, this also suggests that the rate of heat transfer between vapor and liquid for each tray is affected. And the K factor is also affected. Remember the Y equal to Kx. You can check before making a change and after you make the change. You can compare these two curves for the K factor. You can also compare the temperature of the column, the two curves. You don't like the curve, you can use a table. Espen can give you a table for each tray. So there's a table to show you the temperature, to show you the K factor. Or you can also compare the vapor flow rate and the liquid flow rate. Okay, what are the assumptions to take when using the shortcut column to perform sizing? So what do you think? What do you think would be the assumption? Yeah, indeed, the new design objective has 98% purity. This is one change. So Iman, you can consider, just do only one change. You don't like this one, you can consider changing the external reflux ratio. You only need to do one change. Please don't do two changes at the same time. Because the question only asks you to do one change. Come back to assumption. What do you think will be the assumption when using the shortcut column to perform sizing? So my suggestion is that do the internet search. The correlation for shortcut method was developed by Underwood. Underwood, U-N-D-R-W-O-O-D, Underwood. You do a search on this, or go library, look for book, and you study his work more closely. You can find his assumption. One assumption has to do with relative volatility. That is correct. Relative volatility, he's correct. Constant molar flow rate, yes. Anyway, you can do an internet search, look for Underwood. Underwood shortcut method for distillation. In fact, the Aspen simulation is based on the Underwood correlation. Yeah, okay, good. So you're done your literature search. We like students who are more independent, more directed learners. Now, please do your literature search. Don't always look for me for the answer. Okay, so the question is, are the two assumptions sufficient? So these are important assumptions. If you're not quite satisfied with this, then you do more literature search. Anyone got questions on other topics? How about the heat transfer? How about the U0? Any questions on the fouling coefficient? Let's talk about heat exchanger. This morning I mentioned, when do you use square tube arrangement and when you use the triangular tube arrangement? No, you ask a question that's too general. Okay, you have to memorize the Darcy formula, polytropic equation, polytropic compression, but the work input by compressor, that's for reciprocating compressor, and the work done in one cycle, work input for centrifugal compressor, and the work done in one cycle for the reciprocating piston compressor. That set of formula, isothermal, adiabatic, and polytropic, that set of formula you don't have to memorize. Don't memorize those correlations for the heat exchanger. Darcy equation you have to memorize. I mentioned that don't use a formula to calculate the fanning friction factor. The reason is that if you got your calculation wrong, you don't get any mark. But if you use the Moody plot, if you did your Reynolds number correctly, you get 1 mark. Sometimes if you do your relative roughness correctly, you get another mark. But if you use a formula for turbulent flow and calculate the F, if you got it wrong, you don't get any mark. Yes, we assume total condenser and 0 pressure drop across the reboiler and condenser. Indeed, we just ignore the pressure drop across reboiler and condenser. Of course, in the real reboiler and condenser, there'll be a small pressure drop, but we just ignore that. We use a total condenser. We just want to simplify the problem. Otherwise, if you use a partial condenser, then you got 2 products. One is a vapor product, and the other one is a liquid product. And that makes it more complicated. Depends on how the questions is written. So if the question say that this is a total condenser, then don't have to state this assumption. Otherwise, you have to read the questions very carefully. If you read the question very carefully, from there you can figure out whether you need to state the assumption or not. The reason for stating assumption is basically to support your calculation. Right, so this one, the calculation, I already explained this morning, the difference between a bigger K and a smaller K. A bigger K, the VF is bigger, and smaller K, the VF is smaller. But that's in terms of geometry. Bigger K, VF bigger. VF bigger means that no, you can expect the tray spacing to be larger. And this one makes sense because the largest tray spacing means that you can accommodate more liquid. So the tray spacing is higher. Most of the time, the liquid will be here, somewhere here. Liquid will be here. Normal operating condition. Abnormal operating condition, the liquid will touch this tray here, and that is called flooding. But normal operating condition is just above here, and then overflow the vier. Remember that there's a foam. In the class I showed a picture. There's a foam over here because there's a splashing. Similarly, over here it will be foam. It's not a very nice, calm liquid surface. You have a foaming on top because of the because it's a waterfall effect. So create the bubbles. The bubbles when they cluster on the surface, the clustering of bubbles will form the foam. Yes, indeed. Ignore the negative sign for condenser duty. Negative sign means that we are removing the heat from the vapor. So the vapor can now condense to form a liquid. So just ignore negative sign in your Aspen. Okay, let's look at section A, question 4. Explain the basis for condenser and reboiler pressure. The basis here is that condenser and reboiler pressure, they're constant, and there's no pressure drop. Why there's no pressure drop? You expect the liquid to move around a lot inside the condenser and reboiler. Just you expect it to move around a lot. So you don't expect to have too much movement. Although it will be turbulent inside the condenser and reboiler. But as a whole, it's relatively calm, different from the tray. The tray, you have a liquid flowing downwards and the vapor rising. So you can treat the condenser reboiler like a container. As long as there's not too much fluid flow, then you can take the pressure to be constant, relatively constant. Because you treat the condenser reboiler like a container. So not much fluid flow. Condenser, although there's a fluid flow inside, but the whole thing is like a container. Yeah, a lot more room compared to the pipe. You think of a pipe diameter very small. The shell diameter of the shell and tube heat exchanger is much bigger. The pipe diameter much smaller. The smaller pipe diameter means fending friction factor is higher, so the frictional loss is higher. Whereas for big diameter, as in the case of shell and tube heat exchanger, you expect the pressure loss to be smaller. Therefore, we just think that the pressure drop, there will be pressure drop, but it's not significant. So we just ignore that. So the important thing is that you must be able to explain this one, the graph here. What's the effect of change in the density, change in the mass flow rate of liquid and vapor? It will change the liquid vapor factor, FLV. How can the FLV increase? FLV will increase when vapor velocity, or rather vapor mass flow rate, decrease. The V decrease, and the liquid density decrease. The V decrease. The vapor flow rate decrease. The density of liquid decrease. This one smaller, this one smaller. FLV becomes bigger. Become bigger is on the right hand side. You find that the K factor also decrease. Means that when you decrease the vapor flow rate, or when you decrease the density of the liquid, there's a lesser tendency for flooding to occur. Why lesser tendency? Because your FLV increases, your K value decrease. The K value decrease, then what happened to this? Yeah, so this velocity decrease. No, velocity decrease. That is the velocity at the flooding condition. Here, you can see here. So velocity for flooding condition. The velocity for flooding condition is lower. It's lower when the vapor flow rate decreases, or when the density of the liquid decreases. So the flooding velocity decrease. Flooding velocity decrease means that it's easier to reach. In fact, it's easier to reach the VF. So easier to reach VF. And the VF is smaller. The VF is smaller. How to achieve a smaller VF? You need to have a larger diameter, because the area is bigger. VF smaller, area is bigger, diameter is bigger. So in other words, your column diameter must increase. That is to decrease the vapor mass flow rate, the VW. That's the case for vacuum distillation. Because a vacuum, if you operate a vacuum distillation, it's easy. It's very easy for liquid to evaporate. Very easy. So when very easy for liquid to evaporate, there'll be plenty of vapor. But when you have plenty of vapor, your column diameter must be bigger. If you don't have sufficient diameter, your velocity will be very high. Your vapor velocity will be very high. And when you have very high vapor velocity, there's a greater tendency for flooding. And therefore, this one it makes sense. If I have a vacuum distillation, I have a very high VW, very high VW, my FLV will decrease. So it's over here, FLV will decrease, and in general the K is bigger. If K is bigger, then VF will increase. So VF increased. Okay. Yeah. Higher vapor velocity. Sorry, higher vapor flow rate. So FLV will decrease. That depends on the spacing. But in general, the K value will increase. So the VF will increase. So VF increased. That is the vapor velocity at flooding condition. VF increase. I can afford to have a smaller cross-sectional area, meaning I can afford to have a smaller diameter because my VF is now higher. Okay, heat transfer correlation. Now, if you talk about the heat exchanger, you don't have to memorize. You can see the correlation over here. This one you must memorize. This is not correlation. This is an equation for heat transfer. This one you need to memorize. The definition of Nusselt number, Reynolds number, Prandtl number, all this you must memorize. This one no need to memorize. This is a correlation. This one no need. No phase change means there's no evaporation, no condensation. This one no need to memorize. All those correlation. This one you must memorize. This is very important. The equivalent diameter. Very important. And study this one. Look at it very carefully. I mentioned that the small d is for the small pipe. Big D is for the big pipe. DO means outer diameter of the small pipe. This DI means inner diameter of the big pipe. This one no need to remember. And this one no need to remember. This is for the shell side, the flow outside of the tube. No, the number of trays does not include the reboiler. If this is one shell pass and one tube pass, don't use a chart. The chart is for multi-pass. No need to remember this correlation. This one is for the tube. The important part, okay, this one you must remember. This set of formula. This second term here, this is for heat conduction. This is convection, and this is convection. And this is to account for the fouling, inside and outside. It's I and O. Inside the tube, this is outside of the tube. Right, so these are important consideration when you decide on the types of shell and tube exchanger. Okay, this part is important. You have to read this one. This one, considerations, these are important. What you need to consider when you look at diameter, when you look at wall thickness, and so on. Tube pattern, you want to use triangular, square, rotated square. You need to consider fouling, pressure drop, and the ease of cleaning. This is for the shell side. All right, these considerations is for the shell side. And this one also, the tube pitch, this is tube pitch is for the shell side. This is for the whole heat exchanger, diameter ratio 5 to 10. When you answer this type of questions, please check tube length to shell diameter ratio. It cannot be too big, cannot be too small. So look at this one. You try to do cleaning, which is easier for us to do cleaning. So this one is easier to do cleaning, or this is easier to do cleaning, or this is easier to do cleaning, or this is easier to do cleaning. Right. We have fouling. How do you get rid of the fouling? You have to mechanically scrape off the fouling on the surface. You can use a physical method, or you can use a chemical method to clean the outer surface of the tube. Pressure drop. Which one you think have more pressure drop? You look at a triangle, smaller. You expect to have greater pressure drop. This one, more space, you expect to have lesser pressure drop. Okay, this is the shell diameter. Shell diameter will affect velocity, pressure drop, and fouling. Wall thickness of the shell. You're afraid the shell will burst, so you need to consider the tensile strength, the ultimate tensile strength, and the yield strength of the shell. Because you're afraid that this shell may rupture with burst. Corrosion, you're afraid that this shell will be corroded, and then the chemical will leak out to the surrounding. Baffle cut. This will affect your pressure drop, your overall heat transfer coefficient. Similarly, for the baffle spacing, you want the baffle to be very near each other. Then you have a high pressure drop. But you may have a good heat transfer coefficient because you're squeezing a lot of shell fluid between two baffles. But if the baffle is very far apart, higher than the 1 times the shell diameter, very far apart, of course you have a lower pressure drop, but is there good contact between the shell fluid and the outer surface of the tube? And that will affect the heat transfer coefficient. So heat transfer coefficient is dependent on how much the shell fluid is contacting the tube outer surface. This one, the fluid allocation, this one is also important. It's a more corrosive, a greater fouling tendency, higher temperature, higher pressure, put at the tube side. Higher viscosity, please don't put in the tube. It's very difficult for the fluid to move inside the tube. The pump will be overworked. So higher viscosity, put at the shell side. You want lower flow rate, put at the shell side. This one you need to remember. The liquid tube side, 1 meter per second to 3 meter per second. Shell side, 0.3 meter per second to 1 meter per second. But this one, shell side, you must be very careful. You look at the tutorial question. The cross flow area. There's cross flow area tutorial 7. You look at the calculation. You cannot just simply take the pi r square for the shell. The moment you take pi r square for a shell, your answer will be wrong. You have to calculate the cross flow area. You can find the working in tutorial 7. That's for the shell side. That working is for the square tube arrangement. Okay, look at vacuum, atmospheric pressure, high pressure. Look at the recommended velocity. So vapor, you expect to have a much higher velocity because vapor can move a lot more easily. Vapor can flow more easily, a lot more easily, as compared to liquid. Liquid will find it more difficult to move in the shell, in the tube. But vapor can flow very easily. Therefore, you expect higher velocity. Now, pressure drop, that is dependent on the viscosity of the liquid. If it's not that viscous, the maximum allowable pressure 35 kilopascal. This is for the whole. It's for the whole heat exchanger. That's a pressure drop. If your viscosity is between 1 and 10 cp, that is the maximum allowable pressure drop. 101.3 kPa. 101.3 kPa is 1 atmosphere, which is 760 mm mercury. So for this one, the important part is okay, you need to calculate the U and also the area. Our design objective for the sizing, this is a sizing problem. The sizing problem is determine area. What is the AO? What is the total surface area for the external surface? So that's the sizing objective. Rating is different. So rating is to determine the U. That one is for rating. You determine the U. You compare the UC, the clean one and the dirty one. You compare these two. That's when you do the rating, because you suspect there's a fouling. So you calculate the U value. But this is best done using the Aspen, because when you have fouling, internal fouling, in the shell side, in the tube side, you can use Aspen. Now, when there's a fouling, in the actual equipment, you can read the inlet temperature and outlet temperature for the shell side and the tube side. Based on the temperature alone, you can use the Aspen to figure out, is there any fouling that occurs inside the heat exchanger. But that subject is for you to look into when you go to year 3. That's under plant design. You don't have to do optimization. Optimization means in the sizing, you want to make the area as small as possible. When area is smaller, you don't have to buy such a big heat exchanger. Of course, the heat exchanger can be oversized, just like control valve. Control valve oversized is also no good. Similarly, the heat exchanger is oversized is also no good. So we try to minimize this area. So that's optimization. But don't have to do this, but you have to do this in your 3rd year. Then same thing for distillation column. For distillation column, you want to achieve purity 96 mole% for benzene. What is the minimum? What is the minimum external reflux ratio? What's the minimum LOD? Minimum LOD to achieve the 96 mole%. Why you want minimum? Because L over D, minimum means your distillate flow rate is highest. L over D. D is the highest. D is highest is good because you got more production per hour. And at the same time, you can achieve the 96 mole% benzene. That is good. That is optimization. That means you minimize the LOD. At the same time, you maintain the 96 mole% purity for benzene in the distillate. So you optimize, as far as we are concerned, we're optimizing the distillate production rate. Okay, the trial value here, there's no fixed method what trial value to use. You can just follow the methods mentioned in the tutorial. You can just assume maybe 500 watt per meter square per Kelvin, or even 1000. That's perfectly all right. Maybe 500 or 1000. No, don't assume a value is very small. Don't assume 0.5. Just assume a few hundred would do, or maybe 1000. Don't assume 10,000. Not likely that your heat exchanger can have a U value of 10,000. The 10,000 is for saturated steam that's condensing. The saturated steam that's condensing give out a lot of latent heat. Only then you can think of the 10,000 for the HI. Let's say think of the steam condensing inside the tube. Then you can think of the HI, 10,000 watt per meter square per Kelvin. But not all heat exchangers use condensing steam. You should be able to draw this diagram. You see the red one and the blue one. You make sure you know how to draw this. Okay, this diagram here. The red and the blue. Red one is for the steam. Now see that the steam temperature is constant. When it condenses, becomes water. So the water temperature decreases. That's why the arrow is coming down. This one, when all the steam becomes condensate, water condensate, and then the temperature of the water condensate, meaning the water condensate become less and less hot. So it's coming down here. This is different. This one, there's no evaporation, no condensation, this stream here. This is just a stream where the temperature is increasing. It's increasing steadily. And this is when all the steam becomes water and the water temperature goes down. So I strongly suggest that you study the MST questions, look at the answer. You see what are mistakes that we can avoid. You need to be very careful, especially fluid flow. If there's a T joint and that particular T joint is connected to the pressure gauge, remember there's no fluid flow to the pressure gauge. There's no fluid flow. Therefore, please don't consider the HF for the pressure gauge. There's no fluid flow. Okay, that's for the T joint. So there's only fluid flow through the pipe. Even for strainer, you can use the LOD. But again, you need to be careful. Sometimes the questions for pressure drop across a condenser or strainer is in terms of the Pascal. So are you able to change it to joule per kilogram? So this is where you need to remember the format. The format for the Darcy equation in terms of joule per kilogram, in terms of meter, there's a head loss, also in terms of Pascal. So you need to memorize these 3 different formats. So you are given the pressure loss across a strainer, across a T joint, but that is in terms of Pascal or in terms of PSI. Are you able to change PSI to Pascal? And then from Pascal, change to Joule per kilogram. The answers are given in the MST solution, so study that portion. Okay, last questions before I stop the presentation. Right, we spent about 1.5 hours. Okay, one last question. All right, we'll stop here. Class dismissed.